Welcome to the TechViews 10X Explainer series. Copper wiring literally built modern computing. It is the absolute bedrock of the digital age. But inside modern AI data centers, copper has hit a massive physical brick wall. It consumes way too much power, generates way too much heat, and essentially chokes under massive multi-rack AI cluster workloads. The solution here? It isn't faster electrical chips. The solution is ditching copper entirely for pure light.
Just take a look at this shocking reality right here. Right now, data center operators are reporting that interconnects, literally just the physical wiring moving data from point A to point B, are eating up about 30% of the total cluster power in large-scale AI training setups. 30%! I mean, that is power not even going to actual computation. It's just wasted moving data around.
So, welcome to what the industry calls the copper wall, or the I/O wall. As we push toward these massive million GPU AI clusters, electricity itself becomes a severe bottleneck. To put this into perspective, at 800 gigabits per second, a single electrical path requires 16 to 17 watts per port. Push that to 1.6 terabits, and the reach of a standard passive copper cable shrinks down to under 1 meter. You literally cannot build a warehouse-scale supercomputer when your multi-thousand-dollar cables have less reach than a cheap phone charger.
All right, moving on to Section 1. First Principles, Designing Silicon Photonics.
So, instead of pushing electrons through highly resistive copper, the industry is making a massive pivot to moving photons. Optical interconnects deliver ultra-high bandwidth, reaching several terabits per second, along with incredibly low latencies down in the picosecond range. And the best part? Practically zero thermal bottleneck. The physics of light simply doesn't generate the extreme heat that electrical resistance does. This means we can move 100 times more data across compute racks while using over 90% less energy.
Zooming in on the actual hardware here, you'll find these microscopic silicone slot waveguides. These are incredibly tiny. We're talking between 100 and 500 nanometers. Innovative companies like IR Labs are actually using highly compatible silicon manufacturing processes to build what's called in-package optics. Basically, instead of placing transceivers way across the board, they're integrating microscopic lasers directly inside the exact same package as the CPUs and GPUs.
To actually make this possible, engineers are utilizing some incredible advanced packaging breakthroughs. Like, for instance, depositing silicon photonics layers directly onto glass substrates. Why glass, you ask? Well, it offers way better temperature tolerance, durability, and expanded optical bandwidth. By doing this on a wafer scale, we're seeing energy efficiency scale all the way down to a mind-blowing 1.17 picojoules per bit, alongside massive bandwidth density. This effectively obliterates that I/O wall we talked about.
Now, understanding these massive foundational hardware shifts is exactly how top entrepreneurs and operators spot the next multi-billion-dollar opportunities before the rest of the market catches on. If you want to learn how to leverage frontier AI tools in your business, automate your workflows, and build highly profitable digital income streams, head over to techviews10x.com right now. We give you the actionable playbooks and frameworks you need to turn AI into real revenue. Seriously, check out techviews10x.com. The link is right there on your screen. Okay, let's get back to the roadmap.
Which brings us to Section 2, the Industry Roadmap and Co-Packaged Optics, or CPO. The absolute most crucial thing to understand here is that the physics problem of copper is not some futuristic 2027 issue. The industry is aggressively abandoning it right now. Just look at this first half 2026 roadmap. This is the exact moment the ecosystem crosses from proof of concept into high-volume production. In early 2026, NVIDIA's Quantum-X Photonics switch becomes commercially available. By March, IR Labs scales a 1024 GPU rack-scale CPO system. In April, TSMC's COUPE silicon photonics platform enters actual mass production. And then by mid-year, Broadcom ships the world's first 102.4 terabit per second Ethernet switch with CPO. The market is shifting completely, and it's happening fast.
Understanding how all this disrupts the supply chain brings us to what we call the paradox of disruption. On one side, traditional optical module makers, companies like Lumentum and Coherent, are seeing their legacy pluggable businesses get cannibalized. But they've successfully pivoted to become highly critical laser foundries, supplying the high-powered indium phosphide lasers required for these new optical packages. On the other side of this paradox, we have the ultimate bottleneck, TSMC. Because they are literally the only foundry capable of this ultra-precise 3D chip stacking, TSMC absolutely monopolizes the global AI supply chain for advanced packaging.
All right, let's look ahead to Section 3,
The horizon, optical computing, and the post-silicon future.
While co-packaged optics completely revolutionizes how we transmit data, the ultimate endgame here is replacing the electrical transistor entirely. Startups like Lightmatter aren't just transmitting data with light anymore. They are doing actual computation with it. They're already sampling photonic compute units that perform complex matrix multiplications natively, using light. By integrating their Passage L200 and L200X 3D CPU engines directly with customer chips, they're promising up to 100 times improvement in efficiency for specific AI inference tasks. Make no mistake, this is exactly what computation looks like in the late 2020s.
The defining takeaway from this entire sector analysis is crystal clear. As the quote says, the companies that control optical silicon packaging and laser integration will control the infrastructure of artificial general intelligence. Let that sink in for a second. Whoever masters this optical layer is going to dictate the future pace, scale, and power constraints of AGI. It is fundamentally that important.
So, I have to ask you this. If the future of computing runs at the speed of light, are your strategies still running on copper? Think about it. The future of computing doesn't run on electricity. It runs at the speed of light. Head over to techviews10x.com to access our full tech breakdowns and frameworks, and make sure to like and subscribe to the TechViews 10x Explainer series. Thanks for tuning in, and I'll see you in the next one.